โอ้ไม่ Wi-Fi ห้องนี้ไม่แรงครับทำให้ผมโหลดเน็ตอ่อนครับโอ้ต้องมาข้างนอกครับไม่ก็ Okay, good morning, everyone. Welcome you to EGEL501, which is Advanced Mathematics for Electrical and Electronic Engineering. So we are still at the first lecture, which is the first lecture note, which is the Advanced Algebra. And it has also something related to a complex function as well. As far as I can remember. Oh, first of all, I would like to say sorry for being absent last time because there was an urgent meeting between professors from Curtin University in Australia and the professors here, the lecturers here at Mahidol University, because we want to make cooperation between Mahidol University and Curtin University in Australia, especially for doctoral degree students or PhD candidates. Well, if you are interested in this kind of cooperation, they offer, I think, 6-month or 12-month period for you to stay there at Curtin University in order to do the research or write a paper, research paper actually. Well, but to the base of my knowledge, I think you need to be also a PhD candidate. So after you graduate in this level in master degree, you can further continue the PhD period, and then you can go to or you can join this kind of corporation. And yeah, I think the dean of international cooperation of Curtin University was a great person. In yeah, we are waiting for any kind of joint work soon. Okay, I have added a few examples about our Moore-Penrose inverse, right, which is the kind of pseudo-inverse. In engineering, this is the most widely used pseudo-inverse. I don't know. The mouse doesn't appear in projector, so no problem. Yeah, last time we have two examples, right? When the matrix is tall, oh my God. When the matrix is a tall matrix, when the matrix is tall and the matrix is wide, right? You have two cases. You have to apply two separate formula, right? Tall matrix, this kind of thing, right? Like a high building and Y matrix. It's somehow like this, right? Okay. You have to use different way in order to compute the Moore-Penrose inverse or pseudo-inverse. I use the notation of the letters of M and P, so it's straightforward for you to get the idea of what does it stand for. It's the name of the person, two persons who discovered this kind of thing. In example last time is the following. We have a tall matrix which is 3 by 2 matrix, right? And you can get the result like this. This is compute in integer form, which is simple to read, right? But if you go further, it's going to be decimal numbers, right? Another example is the Y case, right? Which is the Y matrix here. It's 2 by 3 matrix, right? Number of row is 2, number of column is 3. And after that, when you use, of course, the tall matrix will go along this way, right? Hermitian first, and then you compute the inverse, and then you multiply it with the Hermitian version. M is greater than N means we have a tall case, a tall matrix. In when N number of column is greater than number of rows, we have Y matrix. In it's the order of the sequence is quite different from the tall case, right? You cannot apply this one, the tall formula to Y matrix. It's gonna be fail, okay? You will not get the result, right? And you will get something like inverse is U condition, or the condition number of the matrix is too high or something like that. It depends on the program, whether you work on MATLAB or you work on Python. You will not get the result at all. And here is the result for the Y case, right? And one of you asked me, what is the property, what is the result or the outcome of Moore-Penrose inverse comparing to the typical inverse, right? The inverse of a square matrix. Well, in the tall case, if you multiply the pseudo inverse with the conventional matrix or the original matrix, of course, you can apply the formula of the Moore-Penrose inverse here, right, in the tall case, and you substitute it to this one, right? This is the Moore-Penrose inverse for the tall case, right? And this is the conventional or the original matrix. And what you can see is that if you look at this product, X Hermitian and X, as if you consider this product as another matrix, let's say it's a product P, okay? P is equal to X and X, okay? It means we have, okay, this is 3 by 2. For example, this is m by n, so it's going to be n times n, right? The number of rows and the number of columns. And here you have m times n, right? So P will belong to the set of, what is that? What is the size of the result here? It should be m times n or m times m or n times n. What is that? What is correct? A, m times n, B, n times m, C, n times n, D, m times m. Which is correct in your opinion? What do you think? Which choice is correct? The outcome here. It's going to be, what is that? A, B, C. The probability of correctness is 25%, right? Which one is correct? Which choice is correct? A, B, C, D. What? From the high school? Huh? C. Okay, our classmates say C, which is correct. Thank you. It's going to be n times n because you have the common number here, m and m, right? Is the product will work smoothly, right? But if those numbers are not the same, you get stuck and the product cannot be computed. So here you have n times n, right? Is it a rectangular matrix or a square matrix? Is it rectangle or square? It's square, right? It's a square matrix. So any square matrix can have a typical inverse, right? The square matrix usually has its own inverse, right, when it is not singular, right? So we can find P inverse, right? P inverse exists. If P inverse exists is a square, right? So we can compute any, we can compute the inverse of any square matrix. So if you look at this, X, M, P, and X will remains a P inverse and P. Is that correct? Because if you look at this here, this is P, right? P is X Hermitian and X. We just introduce a new matrix, which is P, okay? P is a kind of product. So this is P, right? P inverse, right? Because P has to perform the inverse here. And then we have another product, which is P again, right? So P and P will give you, P inverse and P will give you I, right? And because P has the size of n times n, so I here will be of size. What is that? You have n times n and n times n, right? So the I here would be of the size n, all right? In the same way, when you consider the Y case, this one, the Y matrix, it goes in another convention of Morphy-Rhodes inverse, right? We have to follow this way, right? X Hermitian and X times X Hermitian, and overall it's going to be, it's going to need the inverse, right? In the Y case. And of course, if you look at this, X and X and P, you just leave, okay, this X is here, right? And this one, you just, with this one, you just leave its definition, right? Right here, you get the Y case of the Morphy-Rhodes inverse, right? And let's say we have matrix C, matrix C, okay? C equal to X and X Hermitian, okay? And here X and X Morphy-Rhodes inverse for the Y case will remain C and C inverse, right? C and C inverse. So let's talk about the size. X here is of size m times n. And what about X Hermitian? It has n times m, right? So C would be of size, not R, it's C, right? Will be of the size m times m, okay? M is another square matrix, right? So the square matrix would have its own inverse if it's not singular, right? So any matrix with its inverse will give you I, right? Identity matrix. And what is the size of the outcome here? Because C has the size of m times m, right? And here is also m times m. So you can derive there is the size here, m times m. So I identity matrix should have the size of m, okay? That's the way we can approach the result in equation 60 and 61. All right? Is it okay to you to see why we arrive at this? Okay? Let's say because the matrix here is a kind of product, and the product has the square shape, and of course any square matrix, if it's not a singular matrix, it should have its own inverse, and the inverse matrix of a square matrix stay together with the conventional one will be identity matrix, right? And the size is different depending on we consider Y case or tau case. Okay, example of identity matrix is there is invisible. It's invisible. I3 means we have three times of 1, right? 3 times. In of course when X is not a rectangle, when X is a square matrix, can we still compute the Morphy-Rhodes inverse? I show you here in equation 63, when you apply the Moore-Penrose inverse, which is a kind of pseudo-inverse, to any square matrix, when X becomes a square matrix, it means when number of rows is equal to number of columns, it just simply reduces itself to X inverse. How? If you look at this, if you apply the formula of Moore-Penrose inverse, whether it's tau case or the y case, it will give you X inverse. Okay, this is the derivation based on the tau case, I think, right? This is taken from tau case, I think. X, of course. Yeah, now let's move to another property. You may hear it in many research papers, but it's rare. Maybe you cannot see it quite often. The word is called idempotent, right? Idempotent means the matrix, any square matrix. Idempotent holds when you have a square matrix. Idempotent cannot be applied to any rectangle matrix. Okay. If we have matrix X of the size m times n, which is a complex domain, which is on the complex domain. If you multiply X to X, you get simply the result X. Okay. First, let's check whether this multiplication is possible or not. Can we perform X times X when our X is of the size m n times n by n? Is it possible to perform this multiplication? We can do, right? Because here is n times n and n times n, right? So, of course, the outcome would be any matrix of the size m n times n again. And this is a spatial result. Usually X times X doesn't give you simply X, right? But this is a spatial matrix. The spatial property is called idempotent. And you may ask me, what is the case, what is the example for idempotent? Idempotent matrix could be found generally in projection matrix. Okay, projection matrix means you project any right-hand side matrix to the column space. We will talk about column space later in the chapter 2 or chapter 3. You make the linear combination. You know, have you ever heard the word linear combination before? I hope you have ever heard the word linear combination. For example, if you have three numbers, 7 minus 2 and 5, okay, you have three numbers. What is the linear combination? I have to say it here. Linear combination. Linear means it's simple, right? If you have three, let's say this is A1, A2, and A3. A1 is 7, A2 is minus 2, and A3 is 5. What is the linear combination of these A? It means you can place You can say, you can place any coefficient, coefficient, which is constant, right? You can say C1 and A1 plus C2 A2 plus C3 A3. And that's called linear combination. C is a constant, for example, 1, 2, 3, okay? So you're going to have 1 and 7 plus 2 and minus 2 plus 3. Sorry. And the whiteboard is so small in this room. 3 and 5. Okay. Oh, sorry. 5. Okay, this is the result. You can calculate it by your own, okay? Because you are now in the master degree level. Yeah, let's say we compute it. 7 minus 4, 3, right? And 15, and so it's going to be 18, right? So this is a kind of linear combination. But you apply it to scalar. 7 minus 2, 5 are scalar, right? Are a number. Linear combination in linear algebra is that we apply this kind of thing. This is this kind of. So what is the operation inside? What are the operations inside this linear combination? Of course, you have first multiplication, right? You have multiplication because you multiply 1 to the basis, right? Number 7. You multiply 2 with A2. You multiply 3 to A3, which is number 5. Another operation is addition, right? Or summation. Okay, summation. After you multiply, which is number 7, which is minus 4, which is 15, you add them all together, you get 18, right? So there is another operation which is called summation. So in linear combination, we need 2 operations. The first one is multiplication, and then finally summation, right? Actually, you have this kind of experience before, right? But no one talk to you or tell you that this is what you have performed in terms of linear combination. But this is simple because you apply this kind of thing to only a scalar, but in engineering, or when you in a higher level, like in doing the research, it's not going to be the scalars like that. Usually we would work on vector like this, minus 3 and 11, and A2 is 15 and 21, and A3 is 101 and 79, like this, for example. So what do you think? What is the linear combination of A1, A2, and A3 in this case? So you would have like you start from the same formula, which is have you ever heard this kind of thing before in bachelor degree level? No, no? Or is this kind of thing has been taught to you before in the bachelor or no? Okay. You just apply the same formula here, okay? Whether you have 3 vector, 3 numbers, or many, okay? You just apply this kind of thing. Of course, we can still use that. And C1, C2, C3 are constant. It can be any number, okay? I'm going to give you only a few examples. For example, if C1 is, okay, of course, in this case, C1 is 1, C2 is 2, and C3 is 3. What if we have C1 is minus 1, C2 is minus 5, and C3 is, let's say, 4, okay? So the result of this linear combination would be minus 1 times minus 3 and 11, and plus minus 5 and A2, 15 and 21. Okay, and then plus 4. And then 101 and 79. Okay, you can combine this product and summation by yourself. Okay, I assume that you can compute it by your own. But I would like to ask you, what is the style of the result? Is it a scalar, vector, or a matrix? What do you think? The result here will be A, scalar, B, vector, or C, matrix, or D, tensor. What do you think? What do you think then? The result should be A, B, C, D, which is correct? In your opinion, A, B, or C, or D? The result will be C. What I heard is C, right, from you? A, B, or C, or D? Of course, in this case, the result turned out to be 18, right? We say scalar, right? But what about this case? It will be vector, right? So you can compute yourself. Okay. So this is a kind of linear combination. So let's talk about this. A projection matrix means you project A onto A. So it's like you write we talk about geometry. If you stay on the earth like this, okay, and I don't know what symptom you have or what disease you have. You stay like this on earth, okay? You do not stay vertically like this on earth, okay? It's your style or your preference, okay? Let's say the shape that we see you is like this, and you project yourself onto this kind of plane, okay? You stand up like this, okay, in a two-way, and you project the length of your body or the height onto this plane. So the size will be 1. Okay, projection matrix means you project yourself onto the column space or the linear combination of yourself. Okay, and the length will be 1. In linear algebra, it means you multiply A with A of more Penrose inverse, and you may get stuck. The lecturer or the instructor, should we get identity matrix? Should it be identity matrix? Because what I was familiar with before is that A and A more Penrose inverse should return to identity matrix, right? But it's not identity matrix. You will get identity matrix when you talk about the Y matrix. But in this case, we are talking about the tall case. Okay, it's not identity matrix. Why do I say we are considering the tall case? How can you notice I mentioned the tall case? How? What is the reason why I say we are talking about the high matrix case? Because if you look at this formula, this one here, okay, the upper formula, X Hermitian and X inverse and X Hermitian, this is the more Penrose inverse for the tall matrix case, right? And when you apply that to this one, A and A more Penrose inverse, okay, it doesn't give you identity matrix, right? But if you talk about the Y matrix, what is the outcome of this one? If you substitute the more Penrose inverse of the Y matrix case, what is the result then? It will turn out to identity matrix, right? But here, the projection matrix talks about the tall matrix case. Okay, so you can see here it's impossible to get identity matrix. Furthermore, there is another projection matrix, which is called projection matrix onto complementary subspace. Okay, should I write? Yeah. Oh, no. It's better if I write it in good note. Okay, this one is called projection matrix. And onto range space or column space of, I don't know why there is that, okay, of matrix A. Oh my God. Where? Undo. How? How can I make undo. This one, right? Oh, no. Oh. Okay, no problem. Okay, two figure. With two fingers. My God. Okay, thank you. Of matrix A. Okay, and the lower one means the lower one. Okay, this is projection, and this one is called projection matrix as well. Oh. Oh my God. No. Eraser. In this one. Matrix. Onto complementary and subspace of A. Okay. We will talk about the detail of complementary subspace later. Okay. What is the difference? You just subtract the identity matrix, which has the same size of this one. What is the size of this one? What is the size of projection matrix? Sorry, I forgot to talk about it. Of course, A is of the size M times N, right? M by N. And here, you have the size of N by M, right? So what is the size of this product? It will be A is, oh my God. A has the shape of M times N, and then A transpose has the shape of N times M, right? And A Hermitian, what is the size of this one? N times M, right? And what about this? N times N, thank you. Okay? And projection matrix A, which is A and A MP. Of course, you can see that this is of the size M times N, right? And here has the shape N times M, right? Right here. So this projection matrix would be of the size M times M, right? And is that correct? Oh my God. Oh, this is wrong. This is wrong, my God. I think so. Moment. Let me check again. It's wrong. No. This one should not be N. Rather, it's going to be M, okay? AI of the size M. No, it's wrong. It's incorrect. It should be of the size M, because here we have the size of M times M, okay? Well, the projection matrix onto the complementary subspace is just the subsection of identity matrix by a projection matrix, the convention of projection matrix. And that's why we still have the minus sign here between identity matrix, corresponding identity matrix, and the projection matrix here. Okay. Do you want to see how the projection matrix look like? Okay, then I need to show you in an application which is called here Madonna, right? Madonna is like this, okay? Madonna compiler. Okay, you can have it in your iPad or you can simply use Octave online, but this one is more convenient because in this room we don't have a good signal strength for the Wi-Fi connection, right? Okay, let's talk about B and C, right? Oh, okay, this is more Penrose inverse. What is the example? Then we should say, okay, matrix A. Okay, let's say matrix A is tau 1, right? Let's say it's minus 3, 11, and 50, 21, and 101, 79. So our matrix A looks like this, okay? Can you see it? This is too small for you when you stay at the very back side of this classroom. This is still visible to you. Okay, you can see it clearly, right? Let's say our matrix A is minus 3, contains minus 3, 15, 101, and 11, 21, and 79. Well, what about input or source? Okay. What about pseudo inverse? MP. Okay. It is a product, right? A and Hermitian and A like this, right? And inverse means we have to write the power of minus 1, okay? You can also say INV here, okay, without the power of minus 1, okay? You can also simply write INV inverse, which is a conventional inverse for the square matrix, okay? But I prefer to write the very straightforward command, which is minus 1 here. And you have to multiply it with A and, and the Hermitian, right? So this is what we have learned before. It's more Penrose inverse for the tall matrix case, right? And then projection matrix. Let's say it's matrix pi, right? Matrix pi of A means you have to multiply A by A more Penrose inverse, like this, right? You can see here, right? And it's the same as this one, right? Oh, sorry for that. It's too small, right? A and A more Penrose inverse, right? That's the way to compute pi A, which is projection matrix, onto the range space of A. Where? Here. Okay. pi A and A more Penrose inverse, right? Now, you would like to see the result? Yeah. We start with the 3x2 matrix, right, which is a tall matrix, right? And the result turns out to be 2x3, not 3x2 anymore. It's a Y matrix, right? This is the more Penrose inverse. And the projection matrix, why P1? I don't understand. Pi, sorry. Pi, not P1. Okay, and the projection matrix is always square. Okay, it's a square matrix. You can see that the result turns to be 3x3. Okay, it's a square matrix, and that's the projection matrix onto range space or the column space of A. Okay, and what else? What do I want to bring you to? Well, I want to mention that this projection matrix has the idempotent property. It means if it's multiplied, if it is multiplied with itself, it will return itself again. Okay, so I'm going to show you the typical derivation here. Okay, it's a kind of messy, right? It's boring. Anyway, you just substitute the formula of projection matrix A and A more Penrose inverse, and then here again A and more Penrose inverse. Okay, you can group it. You can combine this product, these two matrices as a product, and you can see that this is a product matrix. This is a product. The square matrix and its inverse will give you identity matrix, and identity matrix has nothing, right? We can reduce identity matrix to something without identity matrix, and after that, by considering the definition of the projection matrix, this is actually the projection matrix, and that's why we say the product of projection matrix returns to projection matrix. Okay. Let me ask you, if we have projection matrix like this, and it's multiplied with projection matrix, and it's multiplied with projection matrix, what is the result of this one? What is the outcome? We simply get only single projection matrix. Okay, this is a special property of projection matrix. Okay, this is theory. You may not believe me. Oh, I don't believe you. It may not be true. I cannot track all the derivation or all the detail here. Then I will show you numerically in the program. Okay, you may have the right to not believe me because this is science. Okay, don't believe in everything in what I say. Okay, projection matrix times projection matrix. Okay, I would say double pi. Okay, double pi. And let's see here. Okay, we start with A, right, which is 3x2. In here we compute more Penrose inverse, right, and we compute the projection matrix. And we consider at last the product of two projection matrices, right? and you can see it. The result here is the same as this one. Okay? Everybody is clear now? This formula is, oh, where? Okay. This formula is true. Okay? So you can believe in this theory, not in me, okay? It's true. It's correct. I show you in the program as well. Okay? You can try yourself, okay, by choosing any number here. Okay? You can change it with any number. This property will hold always true. Okay? And I hope you can apply this kind of thing to your work, to your research in the future. Okay, not only that, apart from these products, we have also here, this one. The product of projection matrix onto the lane space of A will yield projection matrix of A. And what about the projection matrix on the complementary subspace? Of course, you just substitute the straightforward definition of the projection matrix onto complementary subspace, which has the, I don't know, the rectangle symbol or perpendicular symbol here. Okay, perpendicular symbol on top. And yeah, coming from the definition, we have the subtraction between identity. Oh, it's not n, it should be, I'm not sure. Why do I write n? It should be m, right? M by n. Yeah, it should be m, not n at all. It's wrong. Okay. Again, here, it should not be n. It should be m everywhere. I will change it later. Okay. M everywhere m. Okay, and yeah, when you substitute the formula of projection matrix onto complementary subspace, of course we have 4 terms of these products, right? 4 terms, 1, 2, 3, 4, right? In the product of identity matrix, it will be identity matrix. Of course, the product of anything with identity matrix will not change at all. Okay, it's going to be m. And of course, you get the result here. And of course, from the former relation, projection matrix twice will give us single projection matrix. It's because it's idempotent. And you have identity matrix, projection matrix, minus, minus, and plus. So this one and this one will cancel each other, right? So the result will be only this, Im minus projection matrix onto A. And of course, it's a projection matrix onto complementary subspace. That's why we prove this product. Okay? The product of 2 projection matrices, whether it's projection onto lane space or projection onto complementary subspace, will return to a single one. Okay. And now it's time to show you in a program, right? Okay. BM pi and perp, okay, perp coming from perpendicular, okay, which is complementary subspace, okay. Pi perp is You know the command in Octave or in MATLAB, it's I, okay, I and of course in this case M is 3, right? Number of rows is 3, number of columns is 2, right? So M is 3. So we write here number 3, okay? And double pi perp, okay? We are gonna say like this. Double pi perp means the product of pi perp and pi perp, okay, like this. And what we expect is that, oh sorry, is not complete yet. Minus bm pi, right? Okay. We expect that the result of this one should be the same as the result of the product, right? Because we are going to prove, or we are going to check whether the idempotent property holds true or not for the projection matrix onto complementary subspace. And you can see here, this is A Moore-Penrose inverse, the projection matrix, and the product of the projection matrix, which is the same, right? And here we compute the projection matrix onto complementary subspace, or we say perpendicular. And the product of these two matrices, okay, you can see that the product is the same, okay? It's the same. And so you can check it in every element, the 1, 1, okay, 2, 1, 3, 1, or 1, 2, okay, 2, 2, 3, 2, or 1, 3, 2, 3, and 3, 3. Okay, you can see all the elements here are the same. So we come to the conclusion that of the complementary subspace, and it should be M, okay? It's not N, that's why I say number 3. We arrive at the conclusion that the product of the projection matrix onto complementary subspace will remain this single projection matrix onto complementary subspace. You may ask me, what is the benefit of this kind of thing in your life, right? Or in doing the research? When you notice this kind of thing, and you derive your own algorithm by using mathematics or anything, if you have product of projection matrix together, okay, when you come to the point that you have the product like this, okay, where is, okay, okay, you study the theory, and you would expect also what is the benefit to you, why you should learn, or you should keep this kind of thing in your mind. Because when you develop a new method in the research according to your advisor, okay, you can apply this kind of thing to simplify your algorithm or your computation method. Okay. For example, if I have a method like this, okay, I have a system, you have a system like this, you input matrix A, for example, and you want to get X, and you arrive at a certain point that you have to compute projection matrix A, and you have to multiply, let's say, matrix B and projection matrix A, and times projection matrix A and another matrix C. Okay, and this is the first step in your algorithm. This is a kind of flow chart. Okay, it's a kind of procedure. There are 3 steps here in this, and then you say this is output. Okay, and you use it for every application. Okay, when you develop a new method and you compute it like this, and if you have never studied this kind of thing before, you're going to leave this burden, this computation burden, to your PC, your personal computer, or to your CPU, right? I'm going to say that if you multiply this kind of thing in like you compute it million times, what is the disadvantage? It's like you carry a heavy stone all the time and you run million times, right? CPU will have burden, right? They have to carry something which is very heavy, right? The good thing when you learn or you study something like this before is that you should not leave it like this, okay? Do not say write the command to your code or to your Python, to your MATLAB like this. Do not say or write something like this onto your script or MATLAB line, MATLAB M file, right? In MATLAB you say M file, right? In Python you say Python script, right? You should not write it like this. The clever person, after learning this, should say B and projection matrix A and C only. Why? Because the product of this thing will be the same as a single one, okay? Why should we compute the product all the time in CPU, right? It may delay your algorithm by, let's say, 3 microseconds. Okay, you know the CPU is very fast, right? But why should we leave this kind of burden to the CPU? Because it's got to consume electricity and it will give delay to your whole process, right? In order to speed up or to make your computation fast, you have to remove this kind of thing to only this, okay? Now you understand why we need to learn something like this, okay? In order to make your computation or your method very quickly, okay? And what is what is the advantage of quick computation or high-speed computation? It's quick, right? Have you ever seen the competition of robot in China? Okay? Because they run like 100 meter, right? In running like the athletes, right? Athletes in real competition. And furthermore, there is hurdle 110 meter competition, right? The robot needs to recognize the object very quickly, right? In order to whether they're gonna make the decision to jump or to cross the bar, right? When they attain the hurdle running competition, right? And if you leave this kind of thing, your robot will be slow, right? Even it's very little, like 3 microseconds, right? But if you compete with another company, if you don't know this formula before, what is the result? Your robot will be slower than another company, right? So I give you the suggestion, reduce this or skip this kind of multiplication to only a single one, like this. Or even in the worst case, if you don't know this kind of thing before, you have to say, let's say, Q and projection matrix A, projection matrix A, and let's say C, projection matrix A, projection matrix A, and matrix S, okay? What happened if you leave it like this? You spend more 6 microseconds, right? For the full formula, right? It's better to reduce this thing to something shorter, right? And that's Q, projection matrix A, and C, and projection matrix S, okay? You save 6 microseconds for the CPU so that your robot will do something quicker, okay, than the full computation here. But we prove that whether you compute the full product or the shorter one, the result will be the same, right? So there is no accuracy trade-off at all. We don't lose any accuracy at all, okay? But we save or we throw away 3 microseconds, okay, without any loss of accuracy. Okay. And if you watch the news, if you look at the news, there is the boxing also, right? Boxing competition of robots, right? And if you are slow, you're gonna die. Your robot will be broken because another or the opponent try to punch you or kick you. You still spend more time and you cannot escape from that urgent time, right? Okay, this is a few techniques that you have to apply to your work if you face or encounter this problem. Okay. Previously we talked about idempotent, right, which is the structure of matrix that returns to itself without the real computation, right? We can save a lot of time. And there is another property which is quite close to idempotent. It's called nilpotent. Okay, this is very rare, I think. Have you ever heard this kind of thing before in your bachelor degree? Idempotent, nilpotent. Has anyone said to you before in bachelor degree? No, right? Okay. What is the word? What is the detail of nilpotent? Nil comes from the word now. Okay. You know this word. What does that mean? It means nothing, right? Nothing or empty, right? Or zero, right? So nilpotent means potential to become zero. Okay? Nilpotent. And what about idempotent? Idempotent. Potential to become identity. Okay? You understand how they form the word? Okay, it's not my language, but I try to give the explanation to you. Okay. So nilpotent comes from the word now or zero or empty set or something like that. Okay, empty set. Okay. So if we have a matrix which is a square matrix. Sorry. Is that correct? Oh yeah. If we have a square matrix, okay. If we have a square matrix like X has a size of n times n, and we have m, small m terms, okay, of X, and when we compute the product, the result turns to be O of n. What is the O of n? It's a zero matrix, okay? And it's a square matrix of size n, let's say O O4, what is that, O4? What is O4? I don't know O4. I know only O2, which is oxygen, right? And O3, which is ozone. What is O4? No. We don't talk about chemistry, okay? We talk about linear algebra. O4 means you have 0, 4 rows and 4 columns, okay? Like this, okay? It's O4. You can adapt yourself to O3 or O2, right? Which is not oxygen, okay? O2 is the 0 matrix of size 2, okay? O4, O5, or O million, up to you, okay? It depends on your works. All right, M is an integer, and the nilpotent property is quite special, okay? O3 is like this, okay? You have 3 rows and 3 columns. All entries are 0, okay, of size 3. Examples of the nilpotent is like this, okay? It's like this. If you have 2, 2, minus 2, minus 2, and, sorry for that. 2 minus 2, 2 minus 2, and if you arrive at something like this, you have, I'm lazy to remove that thing. It's better to use the MIT style. They have different whiteboard. Okay, if you develop a new algorithm, you start here, and your flow chart is gonna flow like this, right? Your whole procedure flow like this. Can you see it? Yes. Okay, thank you. And you do something, blah, 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 okay? And you have, let's say, B minus A, and plus Q and matrix P, like this. And if your A is like that, 2, minus 2, and minus 2, and you program everything like this, okay, to something more, okay, and then you arrive at, okay, N. Okay, you finish your computation, sorry, N. The problem is that at this step, you know that your A is like this, but you have never studied or learned before about nilpotent property. What happens? You just write this kind of thing onto your MATLAB or your C or Visual Basic or what kind of language. And the problem is that the CPU or the computer needs to compute A and A, right? And when you know or you study this topic before, A and A, if you go into the detail, A and A means the computation of these two matrices. You go into the multiplication, this one to this one, right? And this one to this one, okay? And you make the linear combination, okay? This one means number 2, this one means minus 2. You get the linear combination. And you compute it to all 4 elements. And it turns out that we got all zeros. If you don't believe me, I will leave you 5 minutes to get along this, okay? But if you believe me, we go further, okay? Or do you want me to show it in program, in the computation program, or you believe this kind of thing? What should I do? The teacher, I cannot follow, it's too complicated. Then I'm going to show you in the computer program. What do you think? Do you want me to show in the computer program, or you can see it and you can track it. Okay, that's okay. Okay, yeah, you can see that A times A turns to be 0, turns out to be 0, turns to 0. And what happened to our problem? If your supervisor or your advisor asks you to create a technique to compete with the existing method or the guys in other university, if you still code this or write this to M5 or to Python script, you're going to leave a burden to computers, CPU, right? The computer, the compiler, right? So the computer has to compute this kind of thing every time. Let's say you have to do like a million loop. What happens? You will spend like, let's say, again, 3 microseconds times million for only this, okay? This will take 3 microseconds, but if your program has to compute million loops, million times, what happens? You will waste 3 seconds. You have to spend time like 3 seconds to wait for the whole program to finish computation, okay? So is it clever method? No, we have to simply write, we will not write it like this, okay? If I am your supervisor, I'm gonna go back to your computer and change this line to B plus Q and P only. Why? What is the reason behind it? Why? Is that correct? It's correct, but this guy is clever, right? Because he doesn't ask the computer or the CPU to compute this at all, because he knows before that A is nilpotent, okay? The potential to become null, to become 0, to become empty set, okay? So because minus 0 here, even it's a matrix, has nothing to do, right? Minus 0 doesn't change any result at all, right? So you will be stupid if you write this to ask the computer to compute this, okay? Because it has no effect at all to the outcome comparing to this line, all right? Yeah, this is an example of 2 by 2 size. And if you want to see something miracle, okay, it's a matrix of 4 by 4, B, okay? Let's say B is like this, okay? B is like this. And if you multiply B 3 times with 4 B's, you're gonna get 0. And let me ask you, if I have B like that for 7 times 7 matrices of B, what is the result? What is the result here? It should be 3 times of B, right? 3 B's, or it will be, here is 0, right? 0 matrix. 0 times anything will give you 0 also, okay? Something which is, you have to notice whether that matrix is nilpotent or not. But if you have never heard about the word nilpotent, Okay, of course, you can let the CPU compute this kind of thing all the time, a million times, and your algorithm will take much more time than the others or than someone who knows about nilpotent. Okay, this will give you quicker method, okay, in order to compete with other companies or whatever you want, okay. And what about this? C. Do you believe that it's a nilpotent or not? Do you believe it's a nilpotent or? I have already shown you, right? A is nilpotent, A will turn to be 0, B will also turn to be 0. And what about C, matrix C? Because I didn't give you the example to show that you get 0. What do you think then? It's better for everyone because most of you have electronic device, right? Whether it's iPad or computer, right? Would you please download Madonna compiler in iOS for the person who works in Madonna compiler? For the person who works on computer, you may use the MATLAB is also working. Please download. You can use anything, okay? Octave, sorry. Octave is the pronunciation in Germany with my colleagues. In English, we would say octave, okay? Octave. My German colleague, my former German colleague, pronounced it octave because in German they pronounce every vowel. Okay. Please, everyone, download Octave, or you can use www Octave. Okay. I don't know .org or something like that. Okay. Just Google it, and then please show me whether this matrix is nilpotent or not. How? Is everybody ready to code it in the program? Can you? Are you ready to have it? Okay. Or you can use your student. The problem is that in this room, the Wi-Fi strength is not good, right? The Wi-Fi connection is not good. Yeah, you can use also Octave online. You don't have to download it in internet. Okay. I'm gonna bring you to Octave online. Okay, it's like this. Octave online. Like this, okay? And hit the bottom. Oh, okay. Below, at the bottom, you have a command prompt here. All right, right here. How could we check whether that matrix is nilpotent or not? Let's get back to good node, right? We have what is the size of this matrix? It's a square matrix, right? 4 by 4, right? 4 by 4 or 4 times 4, right? 4 rows and 4 columns. In the first row, we have only A, okay? In the second row, we have only B. In the third row, we have only C. And in the last row, we have minus of A plus B plus C every time. So how could we check whether this one is has the nilpotent property or not? Because I didn't show it in this slide, right? The way to do that is the following. Let's say, oh my God, connection is lost. In this room, the internet connection is not so good. Okay, let's say we write it like this. A is whatever number you want, okay? You can choose anything, 1, 2, 3, 4, 5, minus 1, minus 2, any number. Or you can even use the complex number, okay? Let's say I use 3 and what else? This one. And B is 6, okay? And C is minus 8, okay? And then we hit enter button, okay? First of all, we say A is 3, B is 6, and C is minus 8. Let's say, you can check the result. A, what is that? Oh my God. Oh my God, okay. You can check it here. When you type A, number 3 is memorized as A, right? So it will turn to, it will give you number 3, okay? So in the next step, we need to, okay, please come. We have to write the code for matrix C, right? First row A, second row B, third row C, and fourth row minus of A plus B plus C. Okay, write it in this. I hope it's not, it still hold. Okay. Oh, connection lost. My God. What is B? Okay, it's still memorized. All variables are still memorized. So now, that's matrix C, right? I'm not clever, I would say. I would say A, and A, and A like this, right? This is the first row, right? First row. Everyone please do that, okay? Otherwise, you cannot go further with this subject. Okay? A for the first row. Okay? The easiest way is to use, the clever person would use MATLAB. For anyone who didn't use, who didn't have installed MATLAB, okay, you can use the free version, which is this one, okay. Okay, I make a zoom it to you so that you can see it clearly. Okay, A. But what about the second row? The second row is, what is that? B, right? B. What about the third row? The third row is, oh, this guy is clever. You multiply by hands. For A, B, and C, and D, A, B, C, okay? You may need 15 minutes to prove that by hands. Okay, I will show you because now we are in the machine generation, right? We are not in the dinosaur generation. So we have the machine to prove it for us. What about the third row? The third row would contain C, 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 Z, right? The most difficult row is the fourth one, right? Which is minus A, plus B plus C, and that's right. I'm lazy to type it again. My God, can we copy it on this terminal? No, we have to write it by hands 4 times. My God, minus A plus B plus C 4 times. Okay. Minus A plus B plus C in last term, minus A plus B plus C last term, and then close the whole matrix with the square bracket. Okay, like this. Is it too difficult for you? Okay, A, B, 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 C, 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 and minus A plus B plus C minus A plus B 4 times. Okay. All right. Use any language that you are familiar with. You get used to, like in Python, in MATLAB, or in, I don't know, what else? C or Fortran, like my grandfather or something like that. In the grandfather generation, they use Fortran, Fortran. And Fortran has 2 different versions. I think 77 and 99 or something. The commands look a bit different from each other. Okay, now I hope that everyone can code it like this. We're going to check it. This is more mathematician. He proves it by hands. He didn't use computer at all. Okay, he has already showed, try to compute the product, okay, C and C. Okay, now hit the enter button. We get the result like this, which is matrix C, right? This is just an example when you substitute the values of A, B, and C. Okay, you can choose any value of A, B, and C in whatever kind you want. Okay, it doesn't mean that you have to choose A as 3, B as 6, and C as minus 8 like me. You can choose any number, and this is matrix C. Okay, according to the lecture note right here. Okay, here. A, B, C. I just give you an example by substituting the value for A, B, and C. Substituting the value of C, A, B, and C. Yeah, let's get back to the program. I hope the connection is still working. The connection lost. Okay. Yeah, we still get matrix C. And now let's have a look at the product to check whether it has the nilpotent property or not, right? C, okay? And when you hit, okay, we want to see whether the product of that matrix with and itself will remain 0 or not, right? Then we hit the bottom here, okay? And you can see that the result turns out to 0, all 0 matrix. Okay, these hold true for any small a, small b, and small c. I hope everyone can code it, right? Can you get 0? Oh, good. And yeah, answer x times x, can you get 0? Oh, great. And you too, right? 0. Yeah, 0, right?
Not loading.
Okay. Maybe it's a problem of internet connection.
Okay.
It's not strong here in this room. And we are in 2026. There is still internet problem here. All right. Okay. Now, you can believe that this kind of matrix, this kind of structure, has a nilpotent property. Okay. And when you face with or you encounter this problem, the clever person should keep the nilpotent property part in your problem. Okay, don't compute it. Leave only the short version that doesn't affect your result at all. Okay. Okay, now let's move to the next, the more sophisticated thing in this subject. We talk about dot products of two vectors. This kind of thing would be would be something that you have seen before. You may have seen this kind of product before. If you have two vectors, whether it's real or complex, we consider first the real, and we will talk about the complex vector later. When we deal with the real case, the inner product has something to do with the transport operator. Okay, this is the real case, n times 1, x and y. There are two ways to write the inner product. The first one is that we use the center dot here between two vectors. This is the notation that you may have seen before in your high school time, right? And in bachelor degree, we also use the T transport notation. It stands for you flip the column vector of x to be a row vector, and then it's a typical multiplication of vector and matrix, right? y1 and x1 will stay together, y2 and x2 will stay together by using multiplication. And after that, you have to combine all of them by summation, right? And that's the inner product of the real case, right? Okay, do I need to show you the result? Okay. Come. There is internet problem. Okay, it's better I use Madonna. We don't have to wait for the results of the internet issue. Okay, let's say vector A is like this. What is your birthday? 7 June. Okay, 7 and June. Let's say we have 7 and June. So, what about your shoe size? Shoe size. 42, 38. Oh, it's too big, 42. 38, thank you. Okay, then 38. Let's say, I don't know how to get the random number, okay, because my brain is amazed, so tired right now. Okay, 7, 6, 38. And we have another vector, which is B. Let's say, I don't know, random. Okay, random. Round and random. Rand of 3. Okay. And times 40. Okay. Oh, no. 40 times rand. Okay. And oh, no. My God. Okay. 7, 6, and we cannot say 3. Run it. Oh my God, what happened? Oh, okay. Again. Okay, we have two vectors. Oh, we cannot zoom it in this application. Why? Oh no. Okay, we have two vectors, vector A, vector B, 7, 6, 38, and 24, 30, 27. But this number may change later, 24, 30, 27. Okay, I'm going to use the 24, what is that? 24, 30, and 7, or what? 70, or? I cannot remember. My God. Okay, inner product will be how? You can use, as far as I can remember, BM A transport and BMB like this. Okay. What happened? Sorry for that. It should be a column vector. Sorry for that. Okay. Yeah. Here. 7, 6, 38, and 24, 30, 70. And inner product is 3008. It means you have to multiply 7 to 24, 6 and 30, 38 and 70. You're going to get something like this. Okay. That's the inner product of two vectors, like this. Okay. For the complex case, we have to use Hermitian instead of typical transport. Okay. And in Hermitian operator, you have to flip the vector from the column vector to a row vector. And furthermore, we have to leave the complex conjugate to each element. Now, let's have an example. Source. That's the real case, right? Regarding the complex case, I'm going to use also the round random case. Let's say number 9. And plus I times okay, this is another vector, which is vector B, and inner product. The inner product should be Hermitian, right? This is wrong, inner product. Okay, the correct inner product will be with Hermitian. What is the difference between wrong inner product and correct inner product? The correct inner product for the complex, you have to notice that this is the real case, right? Because vector A contains only real numbers, right? And here is the complex case because vector A has real part and imaginary part, right? Real and imaginary part. And according to the theory, inner product of complex system, complex numbers, complex vectors, should perform also the complex conjugate. So it's Hermitian. The difference between transpose and Hermitian is that these one point at that means transpose, okay, transpose, and the command that only means Hermitian. So transpose and complex conjugate. Okay. So I would like to mention to you that you have to use the correct or the proper notation, which is only that here. Okay, not or without the dot symbol. Dot and that means transpose, but in theory we have to use Hermitian, right? Hermitian transpose. So now let's have a look at the result. Oh my God, this is advertisement, my God. Because I didn't, oh my God, how can we remove the okay, here, okay. Yeah. You can see that vector A is a complex, right? It's a complex vector. Vector A is complex. Vector B is also complex, right? Because it has its own imaginary part, like 5i, 6i, and 1i. And when you compute the wrong inner product, by using only transpose, you get the wrong result. And when you perform the correct one by using the Hermitian transpose, you're going to get this. Okay. So please be careful to not use only transpose to the complex case. In the complex case, you have to use the Hermitian transpose, which is only that in MATLAB. We talk about MATLAB or Octave programming. Okay. Now we will see further property of inner product. In quantum mechanics, even not only in electrical engineering style, in quantum mechanics, if you work in department of physics, okay, at Faculty of Science, the people there would use this notation, the inner product between x and y, but the computation detail will be the same, okay? Summation between summation of the product between x and y, but one of them has to do the complex conjugate. Okay. Another, if you look at the research paper in electrical engineering, another notation of inner product of two vectors is like this. Okay, you have the angle bracket x and y. It means the inner product of x and y. Now we will talk about spatial structure of two vectors. When the people say orthogonal to each other, it means those two objects has no relationship in linear algebra. It means it has no relation to each other. A non-zero vector x is orthogonal to another non-zero vector y when their inner product is 0. Okay, I don't know what to say in human. Let's say this person and this person are orthogonal to each other. It means if this person would like to go to the canteen, this guy may want to go to swimming pool. So their direction has nothing to do to each other at all, like something like that. But the way to measure the non-relation or the zero relation in mathematics uses the inner product. So let's say if x is orthogonal to y, it means the inner product between x and y is 0. Okay, is 0. This holds true only not only for real case but also for the complex case. In the complex case, you have to apply the Hermitian transpose operator. Okay. Let me ask you, why do I use typical 0, not the bold-faced symbol 0? Why? Because the inner product will give you scalar, right? So 0 scalar doesn't need the bold-faced symbol, right? But x and y must be non-zero, and that's why I write 0 with straight style, right? With bold-faced font here. Okay. X and y must be non-zero. Okay. And what else? You may ask me, why should I learn this? And does this kind of thing happen in our real world or not, right? What should I say? Do you know singular value decomposition? Have you ever heard this word before? Have you ever read a paper that talks about singular value decomposition? If not, then we will talk about that in chapter 5 or chapter 6 or something like that. Singular value decomposition. Okay? This is too dirty. I have to clean the whiteboard. Okay. Have you ever heard the word moment? Of course, everyone comes from electrical engineering, right? Everyone has already studied or got to know Fourier transform, right? Everyone heard about that, right? Have you ever heard about Fourier transform, right? And in mathematics part, I think everyone would have already heard eigenvalue decomposition, right? You know eigenvalue, you know eigenvector, right? Eigenvalue, oh my God, the wrong pen. In eigenvalue decomposition, you try to solve this problem, right? A minus lambda I equal to 0, right? And similarly, singular value decomposition, this is called EVD, right? And here is called SVD. You can Google it in internet. Singular value decomposition is a basic tool for numerical linear algebra. In in eigenvalue decomposition, you can decompose matrix A to E and lambda and E, right? And this one is -1, which is inverse, right? E contains eigenvector, right? Sorry. Otherwise, I'm going to say something wrong. It's better to look at the detail, the correct theory of eigenvalue decomposition. Oh my God, internet connection here in this room. Sorry for that. No. Dead determinant or A lambda equal to AE equal to lambda and E, right? You solve this problem and you gotta get this kind of thing, and you get E1, E2, blah, 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 En, and then you get lambda 1, lambda 2, blah, 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 lambda n, right? You get E1, E2, blah, 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 En, and -1, right? Yeah. But in singular value decomposition, you have A, okay? This is what you may have seen in bachelor degree. The second one is singular value decomposition. If you have matrix A, it can be decomposed to U. This is matrix U, okay? Matrix U and sigma and V, and then Hermitian. Okay. This can be performed to square matrix only, okay? You can apply this to square matrix, right, in your bachelor degree. As I said before, in master degree, you're going to need to face with something more difficult. In singular value decomposition, you can apply this kind of decomposition to one. The first one is rectangular matrix. And you can also apply it to square matrix as well. Okay, but eigenvalue decomposition in your bachelor degree can be used for only square matrix, but this one can be applied to whether you have rectangular matrix or square matrix, it works, okay? But in this one, if you have rectangle matrix, you cannot apply eigenvalue decomposition to get this thing. Okay. Why do I bring you to singular value decomposition? Because I'm going to show you how the structure of matrix U is. Okay. Matrix U contains U1, U2, blah, 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 until U Mn, right? Mn. M. Okay? And sigma contains, it's difficult. I will not talk about sigma. It's too deep. Okay? We will see it. You will see it later in chapter 5 or chapter 6. It's sufficient now to talk about only U or V. Okay? U1 and U2 and UM has its own property which corresponds to this thing. U1, U2, and UM are orthogonal to each other. Okay? U1, U2, and UM are orthogonal to each other. Okay, that's the reason why I want to introduce you to this you to SVD, because I will show you this an example to this orthogonal property. Okay, we still have 30 minutes, right? That would be sufficient for me to show you an example. Now let's move to the programming language, Octave or Madonna or whatever you want. Okay, B, M, A. Okay, now to be fair, I must ask you, what is your birthday then? Birthday? 10 and 5. And your shoe size? Shoe size?
32.
32.
Yeah.
Huh? 32, very small.
But I think
32. Okay, whatever you want. I believe you. Okay, I believe in you. And you, what about your birthday and shoe size? 14, 1, and shoe size? 42. Okay. And the next person, birthday and shoe size? 6, 7, and 42 again. 42 too. And need more one person. Who would be the candidate? One more person. Okay, this guy. 7-Eleven is the name of convenience store. Right, convenience store. 7-Eleven and shoe size, please. 43. Okay. Now we have a matrix A like this. Oh my God, error. Why? What? Oh, moment. I forget the equality size. Okay. We have a matrix A like this. 10, 14, 6, 7, 5, 1, 7, 1, 1, 32, 42, 43. Okay? So what is the size of A? 4 by 3, right? 4 by 3, 4 times 3. So is it tall matrix or wide matrix? Tall matrix, right? Because 4 number of rows is greater than 3, which is number of columns, right? So I'm going to bring you to SVD. Okay? How? Okay, we will write it, if I remember properly, BMU equal to, sorry, U and BM sigma and matrix V equal to SVD of A. Okay? Okay, if you cannot follow me, you can go to YouTube and watch it later, okay, while you own. If I am too, I go too, with too much speed, okay? If I go too fast, you can follow it in YouTube. So, if you look at the formula like this, okay, A equal to U sigma V, the implementation version is BMU. U sigma V equal to SVD of A. Is it understandable? Does it look okay to you? Yeah. This is the theory. This is the way we usually program it in computer. SVD, okay? SVD. What does SVD mean? Singular value decomposition, okay? And if you want to apply EVD, eigenvalue decomposition, you can also use the composition, but I will not show you the eigenvalue decomposition, okay? Because I want to bring you to SVD because it has the orthogonal property, which is what I'm teaching now, okay? SVD like this. I hope it works. Long time I didn't use it. You undefined, my God. Moment. What's wrong? Should I say something like this? Okay. Now it works. Sorry, long time I haven't used this command before. Okay, you should have also the square bracket. Okay, this is input, this is output, but output will come with three metrics, which is U, sigma, and V. Okay, and when you hit the enter button, you get 3 output as well, okay? You would have the size of, before we have 4 by 3, right? This is of the size 4 by 4, which is M by M, so M times M, okay? And sigma would have the same shape as A because we have 4 by 3, right? So sigma has also 4 by 3. And V, where is V? V stands up here, okay? V has a size of N by N, which is 3, okay? 3. You can see V has a size 3 by 3, or 3 times 3, right? 3 by 3, okay? Should I write it? This is, oh my God, the same color, my God. This is of the size M by M, okay? Here is M by N. Here is N by N, okay? And in this application, we have 4 by 3. Here is 4 by 4, 4 by 3, and 3 by 3, okay? But that is not what I'm going to mention yet. I just introduce you first to SVD, singular value decomposition, okay? The nice thing or the beautiful thing about singular value decomposition is that you can see here, this vector, this column vector is orthogonal to the rest. as I said here, U1, U2, and UM are orthogonal to each other. What does that mean? It means if you compute the product between this one and this one, the result will be zero, right? Like it's like okay. If I project myself, if I am a straight line, okay, here, that is a lamp. The lamp project myself, which is line without width. Okay, now I have width of my body. Or okay, this is the lamp project me onto the floor. What is the length of my body? It's going to be zero, right? Let's say my body is a straight line. Okay, the lamp project, and if you look at the shadow onto the floor, there will be no length at all, right? Because we say usually if you start from your primary school, your primary school teacher would say the line usually has zero width, right? So if the lamp project that line, the straight line, onto the floor, which is 90 degree, this line is aligned with 90 degree to the floor, which, let's say, simply speaking, it's orthogonal, right? Is there any blue or straight line or something like that? Okay, this pen would be better. Or broom. This one. Sorry. Sorry to use the dirty device. Okay, this may give you, may make you confused. Okay, it's better to use the pen. Okay, let's say this is the floor, okay, and here we have the lamp, and here is the pen. The pen can be considered as the straight line, okay? The lamp emits the light, and we try to measure the shadow, the width of the shadow of this pen, right? You can see that the shadow will appear here as the dot, all right? And if you use the ruler to measure the length of this dot, you will get 0 centimeter, right? Because dot doesn't have any width, right? It doesn't have any length, right? Usually the dot is like that. But if you rotate a bit the pen here, if you rotate, now the shadow of this pen will no longer be 0, right? If you rotate the pen, the lamp will emit the light, and this area will appear as the shadow of the pen, right? And you place the ruler to measure the length of this shadow, and that's the projection of the pen onto this line. And you can see that the angle here, I need the green. The green, yeah. You can see that the angle here is not 90 degrees, right? When this line doesn't situate with 90 degrees of with respect to the floor, we're gonna be able to measure the length. The length of that projection will appear, right? But if the angle between this line and the floor is 90 degrees, we will not see any projection length. Is that correct? And in this case, when it's situated with 90 degrees, the people in Greek era say it's orthogonal. Okay? The scientific word in Greek generation say this line and this floor is this line and this floor are orthogonal to each other. Okay, orthogonal means this line and this line has 90 degrees to each other. Okay, and that's why they use this symbol. Okay, if you have a question, just raise your hand if you want. And what does that mean? What is the important thing to us? In SVD, this vector, you know vector, right? Vector can have any direction, right? Right? Vector can go to any direction with its length. This vector will be orthogonal to this vector, and this vector, and this vector. Do you believe that? Okay. This vector will be orthogonal to this one, to the third, to the fourth as well. This vector will be orthogonal to this one, and to this one. This vector will also be orthogonal to the first three vectors. This is the nice and beautiful thing of singular value decomposition. Or what does it give us? It gives us the basis of the direction staying inside matrix A. Okay, like it's like you have a group of people and you want to find the dominant persons in that group. Okay, and maybe we are 20 people, and when we go to any place, there will be only 4 dominant people, like this guy, and this lady are the 4 major persons in this group. Okay, and and 4 of them are, simply speaking, are independent from each other or are orthogonal to each other. If you project this one to this one, there will be nothing. It will give you 0. Okay? If you project this one to this one, it will give you also 0. Now it's time to show you how we can measure the orthogonality between those 4 vectors. Okay. Now, I'm gonna separate those 4 vectors to separate name. Okay. One is U, and if I remember properly, comma and 0, if or 1. Okay. Oh my God! Advertisements again. Oh no! It's advertisement. I didn't register. Okay, I didn't pay it all, so that's why it's free. Free license come with advertisement. Oh wait, my God, how? Okay. Now we try to take each column vector of U to a separate name, like BMU1, which is the first column of matrix U. Okay, matrix U has something like this, and we try to collect this area to the first vector U1. Okay, and now we will do it also to vector U2, and you have to change the index from 1 to 2. Okay, you get something like this, right? Here is matrix U. U1 is like this. Okay, we collect it to vector U1. we place the second vector as, we name the second vector as vector u2. Okay, you can see that I take this area to a new separate vector. And now we are going to, we want to show whether vector u1 and vector u2 are orthogonal to each other. What is the way that? Okay, check orthogonality. Check is equal to BM U1 and Hermitian and BM U2. All right, we're gonna check whether U1, we're gonna check the inner product of U1 and U2. Okay, if both are orthogonal to each other, the result should be, what should the result be? It should be 0, right? But if it remains like number 1 or 2 or 3 or 4, then those two vectors are not orthogonal to each other, okay? Okay, do you want to type it according to this command? I'm going to wait for you. If not, then I hit the enter button easily. Quick. Okay. Okay, now let's see the result. We are running out of time. Okay. This is vector u, right? As I told you, u is the first element in SVD, right? U. We want to check whether u1, u2, and the remaining u are orthogonal to each other or not. Now we take the first vector as u1, the second vector, the second column of u as u2. Now we compute the inner product, and the inner product turns out to minus 5.5511 tends to minus 17, 10 to negative 17. Is it 0? Is that 0? 0 or not? You may say, oh, teacher, it's not 0. It's something blah, 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 minus 5 is not 0. In the last lecture, I have told you that there is something called round off error, right? Because the memory in computer is not long enough because they have a finite block of memory. And that's why we get something very, very low, 10 to negative 17, which is almost 0, right? So it means the inner product between U1 and U2 is what? Is 0, right? When the inner product is 0, we say that U1 and U2 are orthogonal to each other, right? In ภาษาไทยนะครับภาษาไทยจะเรียกว่าตั้งฉากกันใช่ป่ะตั้งฉากกัน orthogonal to each other. Sorry to say it in Thai, so that you can remind yourself from your secondary school. All right. I would ask you to perform something nearly the same. Please check whether the fourth column and the third column are orthogonal to each other or not. Third and fourth or fourth and third is no problem. Please show me whether the fourth and the third column are orthogonal to each other or not. Please show me that, oh, it's too small. How can we make a zoom to this one? It's too small. Otherwise, I'm gonna, but, okay, the instruction command is like this, okay? The instruction or the command are like this. Please check whether the fourth and the third columns are orthogonal to each other or not. Don't believe me, okay? I say that U1, U2, and the last U are orthogonal to each other, right? Don't believe me. Please check whether the fourth and the third are orthogonal. The first and third U's are orthogonal to each other. Show me, please. Okay, when you are able to show me, then say the result to me, please. Yeah. So the result is, 10 to minus 16, right? It's almost 0, and it's actually 0. So you can believe me now in what I say. U1, U2, and every U are orthogonal to each other because the inner products are 0, right? In theory of singular value decomposition, furthermore, they say that the column vector of V, now we move to the right-hand side, not the left-hand side vector matrix. We talk about the right-hand matrix, which is matrix V, okay? They say also that, where? Okay. They say V, which is V1, V2, and blah, 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 until Vn. They say also that V1, V2, blah, 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 until Vn are also orthogonal to each other. Please show me that V, all of these V are orthogonal to each other. Please give me an example whether this sentence is correct or not. The command for U is like this, right? For matrix U is like this. Can you change it to check the orthogonal property for matrix V? Is it correct that matrix V is also give us orthogonal vector? V. Sorry, you cannot see it. My God. It's because there is a light reflection, right? Like here, you cannot see it. Sorry for that position. I have to write it here. Okay, I don't talk about eigenvalue decomposition so much because this is what you may have seen in bachelor degree before, right? Matrix V, which is on the right hand here, can be written as V1, V2, blah, 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 until Vn, okay? Please keep in mind that the last U is Um. The last V is Vn, okay? And from the book from the theory, V1, V2, and Vn are also orthogonal to each other. Okay? And now I request you to, I ask you to show that V1, V2, or any V, any pair of V's can give us zero inner product or not. Can we get zero for the inner product of V? Is it possible to get the zero inner product for V? You compute U1, U2, right? But what about V? What about V? That might not be so difficult, right? You just change the letter U to V, right? Just change the letter from U to V, right? U to V, and then see the result. Should I do it for you here? Okay. The way to do that is quite simple. Just copy it. Okay. Now we change U to V, right? Everything here, V. Oh, now the time is over. Check orthogonality of V, right? Now we run it. Okay. This is orthogonality of U, right? 10 to negative 17, which is already 0. And now we move to orthogonality check of course, this is matrix V. Is 3 by 3 matrix. And V1, just take the first column of matrix V. V2 just takes the second column of matrix V. And now we may compute the inner products of V1 and V2. You can see that the outcome turns to be minus 6.2, 10 to negative 17. It means V1 and V2 are orthogonal to each other. Okay? And the time is over. I must close the lecture now. And we will continue the next property, which is quite similar. It's called orthonormal. What does that mean, orthonormal? I have to introduce you to norm, right? Norm, the way to measure the length of a vector. Okay, there are several kinds of norm. Okay, today is over. Thank you very much. Bye bye ครับ สวัสดีครับ